In the previous segment, we studied a causal structure with common causes. Now we're going to study a causal structure with common effects. So let's consider a graph in which the variables a and y have a common effect, L. For example, we can have three binary variables where a is a genetic factor, you either have it or not, 1, 0. Y is an environmental factor, you either have it or not, 1, 0. And L is cancer. There is an arrow from A to L because the genetic factor increases the risk of cancer, and there is an arrow from Y to L because the environmental factor, say exposure to high levels of air pollution, also increases the risk of cancer. But there is no arrow from A to Y because the genetic factor doesn't have any effect on your exposure to air pollution. We draw this DAG using our expert knowledge. We didn't use any data. What if we had data? Well, when we can data, we can compute the association between A and Y. If A doesn't have a causal effect on Y, as we see in this graph, where there is no arrow from A to Y, do we expect to find an association between A and Y in the data? And to answer this question, we go to our database with millions of people. For each person, we know whether they had the genetic factor A, whether they have the environmental factor Y. Now, we can compute the association, but what does an association between the genetic and the environmental factor between A and Y mean? We go back our definition of association. We know that the genetic and the environmental factor are associated if the proportion of individuals with the environmental factor is different among those with and without the genetic factor. Another way to say this is that the genetic factor A contains information that allows us to predict the environmental factor Y better. If that's true, then there is an association. So, under our graph with no arrows from A to Y, but arrows from A and Y to L, do we expect to find an association between the genetic factor A and the environmental factor Y? Well, according to this graph, an individual's exposure to high levels of air pollution was not affected by her genes. The environmental factor is distributed in the population independently of genes. Therefore, learning that an individual has the genetic factor does not provide any additional information regarding her environmental exposure. Think of it in this way. If we know that 5% of the population are exposed to high levels of air pollution, then 5% of the population with the genetic factor are exposed to high air pollution, and also 5% of the population without the genetic factor. Learning that the person has the genetic factor does not provide any additional information regarding her chance of having the environmental factor. Therefore, there is no association between A and Y. A and Y are independent. Graphically, this means that the presence of a common effect of A and Y does not create an association between A and Y. That both the genetic and the environmental factor may cause cancer in the future does not imply that the genetic and the environmental factor are associated today. And this is another example of how DAGs are both causal and statistical models. When we use our expert knowledge to draw a causal graph with no arrow from A to Y and with a common effect of A and Y, we were also drawing a statistical model that says that A and Y are independent, that they are not associated. More generally, a rule of graph theory is that common effects do not create an association. And that is in contrast with what we saw in the previous segment when we saw that common causes create association. By the way, the common effect L is referred to as a collider. A collider because two arrowheads collide into it. Informally, colliders block the flow of association along the path that they lie on. So far we have considered the marginal or unconditional association between A and Y. Now we are going to consider the conditional association between A and Y within levels of L. For example, we are going to ask the question, is there an association between the genetic factor and the environmental factor among people with lung cancer, among people with L equals 1? And to answer this question, we need data on A and Y and L. Suppose, again, we have our database with millions of people, and for each person we know whether they had the genetic factor, whether they had the environmental factor, and whether they developed lung cancer. With this data, we can answer the question on whether A and Y are associated conditional on L equals 1. To do so, we restrict the analysis to the subset of individuals who developed cancer. Again, we use a square box around a variable to indicate that we are conditioning on that variable. Now we can check in the subset of the population with cancer whether there is an association between A and Y, between the genetic factor and the environmental factor. We just check whether the proportion of individuals exposed to high levels of air pollution is different among those with and without the genetic factor. If the proportions are different, we will say that there is an association between A and Y conditional on L1. Or another way to say this, we will check whether A contains information not already included in L that allows us to predict Y better. So if the correct DAG is the one with the arrows from A and Y to L, but no arrow from A to Y, do we expect to find an association between A, the genetic factor, and Y, the environmental factor, among those with L equals 1, cancer? Let's think about this. Let's say we know that someone has cancer. Now we learn that the person does not have the genetic factor, but she has cancer, so something must have caused the cancer. If it wasn't the genetic factor, then all other causes of cancer become more likely to exist. One of those causes is air pollution or any other environmental factors. Therefore, if someone has cancer L, but not the genetic factor A, then that person is more likely to be exposed to high levels of air pollution. Not because the genetic factor protects against the environmental factor, but because cancer is present and something must have caused it. When we restrict the analysis to people with cancer, the proportion of people with the environmental factor is higher among people without the genetic factor than among people with the genetic factor. We do expect A and Y to be associated even though A has no causal effect on Y. Think of it in this way. If we know that 5% of people with the genetic factor are exposed to high levels of air pollution, then when we select only those with cancer, we should expect more than 5%, perhaps 10%, of the population without the genetic factor to be exposed to high air pollution. If you learn that someone with cancer does not have the genetic factor, it is more likely that she will have the environmental factor. There is a conditional association between A and Y within levels of L. In this case, it is an inverse association. Not having the genetic factor A is associated with having the environmental factor Y among the selected group with cancer. And this association is a bias. When we are using data to estimate the causal effect of A on Y, then any association between A and Y that is not due to the effect of A on Y is considered systematic bias. In particular, in this case, when there is a component of the association that is due to selecting a subset of the population, we say that there is selection bias. In this example, a naive investigator might conclude that having certain genes protects against air pollution because genetic factors and environmental factors are inversely associated among people with cancer. And that would be an example of a biased effect estimate. An important goal of causal inference is to eliminate selection bias. This is another example of how DAGs are both causal and statistical models. When we used our expert knowledge to draw a causal graph with no arrow from A to Y and with a common effect of A and Y, we were also drawing a statistical model that says that A and Y are not expected to be independent, that they are expected to be associated with all or some levels of L. More generally, the graph theory rule says that we cannot exclude an association between A and Y when A and Y have a common effect L and we condition on that common effect, even if there is no arrow from A to Y. Informally, we can visualize a flow of association between A and Y through the condition on L. Let's say this again, because this simple graphical rule is related to selection bias and therefore is very important for causal inference. In fact, we are going to have a full lesson on selection bias later. Conditioning on a common effect of A and Y makes us expect an association between A and Y, even if A doesn't cause Y. And before we said that L was a collider. You can see that colliders behave exactly the opposite as all other variables on graphs. When they are not conditioned on, they block the flow of association through the path that they are on. But when they are conditioned on, they do not block the flow of association. And this graphical rule about conditioning on common effects applies to all common effects, whether they are colliders or they are not colliders. For example, consider a DAG in which we add a variable s with an arrow from L to S. Now S is a common effect of A and Y, but it's not a collider. S is the effect of a collider. For example, let's say that S is lung surgery, which is often a treatment for lung cancer. So do we expect to find a conditional association between A and Y within levels of S? To answer this question, we can use the same line of argumentation that we used when we consider a conditional association within levels of L. Suppose that someone had lung surgery, S equals 1, well, something must have caused it. If it is not the genetic factor A, then all other causes of lung surgery, including the environmental factor Y, become more likely. Therefore, we expect to find a conditional association between A and Y within levels of their common effect S. Selection bias will arise whether we condition on a collider or on something affected by a collider. And we are now ready to summarize all the graphical rules that we have learned.